Well, it's a great privilege to be here. I'm back in Krakow and to be with you all, so thank you very much for the invitation, really much appreciated. So I want to talk about the nature of causality in complex systems. And this is the summary of what I'm going to be saying. I'm going to talk about the hierarchy of complexity, how physics underlies all, then computers and non-physical causes, top-down action in physics and biology, context matters. Physics does not dictate, it facilitates higher causation. The nature of causality, Aristotle was right. When does top-down causation take place? An unpredictable emergence of complexity in the universe. Now, I may not finish that all, I might run out of time, but I'll go as far through as I can. So, the context is the hierarchy of structure and causation. Particle physics underlies atomic physics, underlies chemistry, biochemistry, cell biology, botany, zoology, physiology, psychology, sociology, economics, and politics. It's not just a question of scale, it's a question of causation. What is the higher level of causation? That's the hierarchy that we want to understand. And the view from Newton and Laplace is physics underlies all, the world is determinate. We've got Newton's second laws of motion. So given the forces and the initial data, given the initial positions and the velocities, you can calculate the outcome and everything is determinate. And many people believe that applies to everything, including the human mind. I can quote some eminent colleagues who believe that. Now, Poincaré, of course, said not so fast. If the equations are chaotic, the outcome is unpredictable in practice, but that's not particularly important for what I want to say. What I want to, chaos theory does not really impact on what I want to talk about, which is how genuine complexity emerges. Now, bottom-up emergence is when what happens at the higher levels is controlled by what happens at the lower level. So microphysics underlies macrophysics, and every physics student has learned how kinetic theory of gases shows how pressure and density emerge from the underlying molecules. The theory of solids, how conduction, thermal capacity emerge from the electrons in the band structure of metals. Physics underlies chemistry. The nature of the chemical bond is explained by quantum physics. Physics and chemistry underlying the function of the brains, that neurons are in some sense the cause of our behavior, and higher level behavior emerges from lower level laws in each of these cases. And so you have this idea of bottom-up causation in this hierarchy. What happens below determines what happens at the higher levels. That happens between each levels, and therefore, in principle, some people claim if you understood particle physics enough, you could predict sociology, economics, and politics. Well, some people, they say that in principle you could do that. In practice, the data is too complicated, but nevertheless, they claim this is possible in principle. Now, I'm going to use computers as an example to show how this is not the way things are. So in computers, it's a very, very nice example because computers are the ultimate in mechanistic thinking. You have presumably superstrings underlying quarks, underlying nucleons, atoms, transistors, resistors, capacitors, logic circuits, registers, the arithmetic logic unit, primary memory, the bus, the CPU, memory circuits, the motherboard, memory banks, the computer, the local network, the global network. You have this hierarchy in computers. And the question is, what determines what happens in this computational hierarchy? And of course, the hardware does not determine what happens. The hardware sitting there will do nothing until you load software into it. So it's software and information that make things happen. The hardware facilitates it, but they, in the end, do not cause what happens. What you have is that you have the device level, the digital logic level, the microarchitecture level, the instruction and architecture level, operating systems, assembler language, problem-oriented language, and applications programs. That's the control structures. And on the right-hand side, you have the states of transistors and connectors, of gates and registers, the microprograms, machine language, virtual memory, symbolic names, classes and objects, and data. So you have a hierarchy of the logic on the left and of the data, the information on the right. And what determines what happens is the software tells the hardware what to do in the context of the given data. The specific program and data loaded drive causation. Now, this is obvious. If you change the program at the top, change from a word processing program to a music program, the whole thing operates in a distant way. So it is the software telling the hardware what should happen. So in fact, this is a top-down process, because if you ask which part of the software is the one which is driving the causation, it is a downward one. The application program drives downward to the digital level and the device level. Because, as I've said, if you load different programs at the top, the causation embodied in that high-level program cascades down and tells the lower levels what to happen. The high levels drive the lower levels. It is the logic embodied in the algorithms at the high level and the way that the data is handled at the high level, which in effect, in the end, tells which electrons to flow where in the gates at the bottom level. The lowest levels implement the abstract logic embodied in the higher levels, and they do so through arbitrary codings. Okay, so, and what one should remember here, in this hierarchy, one of the amazing things in computer science, all the higher levels are virtual machines. In that hierarchy, you have the Java virtual machine, for instance. They're not physical systems. And the computer scientists talk all the time about this hierarchy of virtual machines. They're not physical machines. They're abstract machines implemented in terms of the lower level software, which in turn runs on the hardware. So the bottom level physics enables this, but does not control what happens. The software, the abstract entities, shape the cause. And I want to emphasize this. A program is not a physical object. You can't point at it sitting on the table. It is embodied in physical ways. You can store it on a CD disk. You can store it in a flash drive. It is not the same as any of those instantiations. The program itself is an abstract entity. Physical, and so what the computer tells us, although people don't normally think of it this way, is that physical entities are not the only things with causal powers. The same program can be written in many different languages at the different levels. They're representations of an abstract entity. One of the key things, given a high-level program, let's say Microsoft Word, you can implement it on different microprocessors. The same high-level program results in different configurations at the lower levels, but they have the same higher-level logic and output. So there are many different ways this can happen through different microprocessors, and this is a key thing that happens in top-down causation. The high-level logic drives it. There are many different possible lower-level implementations. They all give you the same higher-level outcome, and that's because it's the higher level which is shaping what is happening. So let's look at top-down action in physics and biology. And the key point is that context matters. In the hierarchy, here, as well as in computers, there's top-down action. Now, top-down causation happens by setting constraints for lower-level causation. The higher level structures channel the lower level interactions while respecting the lower level physics. And paradoxically, this restriction creates new possibilities. If you have a gas, there's random motions taking place, there's no restrictions, and nothing very interesting comes out of it. If you have a network of channel interactions, it is the channeling which constrains things, which creates much more complex possibilities. That's the wonderful paradox of what's happening. So reliable behavior of complex systems arises from carefully designed complex structuring. The details matter because they change the microbehavior. If you cut one of those circuits at a key place, the whole thing will stop functioning. So in a complex system where you have this interaction between bottom-up and top-down processing, the micro details matter. We're unlike a gas, the micro details do not matter in a gas. And so, because the micro details essentially alter the macro behavior, you can't coarse grain to determine macro level behavior. The statistics mechanics will not tell you the outcome. So these are examples of these complex systems. It's the details of the microstructure which controls the macrostructure, and then the macrostructure acts down and tells the microstructure how to operate. Now, I think it's very helpful to ask what kinds of top-down causation are there? And I claim there are 5 different types of top-down causation: algorithmic, non-adaptive information control, adaptive selection, adaptive information control, and intelligent top-down causation. And I'm going to talk about each of these in turn. I will give you examples. I could give you many, many more if time allowed. So the first is algorithmic top-down causation. This occurs when high-level variables have causal power over lower-level dynamics through system structuring, so that the outcome depends uniquely on the higher-level structural, boundary, and initial conditions. The lower-level variables determine the outcome in an algorithmic way from the initial and boundary conditions as a consequence of the higher-level structural relations. And this is purely algorithmic. The example, which is just one of many, is synthesis of light elements in the early universe. The amount of helium produced in the early universe depends on the rate of change of temperature in the expanding universe. That's controlled by the gravitational equations and the average amount of matter in the universe. The average amount of matter is a cosmological level variable. That determines the dynamics through Einstein equations. It determines how temperature varies with time, and that changes the nuclear reactions at the lowest levels. So quantities defined at cosmological level control products of detailed nuclear reactions at the micro level. Then again, the example I've already given, algorithmic computation procedures in a digital computer that proceed on the basis of initial data only. The high-level program drives the low-level interaction. So those are two examples of algorithmic top-down causation. The mathematics is the mathematics of partial differential equations, of ordinary differential equation systems, and of computer science. And so it's all well-known mathematics, in all of which, of course, the initial data plus all the boundary conditions determine the outcome. The second kind of top-down causation is non-adaptive information control, and this is a cybernetic system. So this is when you have a system state which is compared with the goals. If they are different, an error message is sent to a controller. The controller changes the system state, and then you compare it again. And the classic example is a thermostat. And the difference from the previous one is information is causally used. Information flows from the comparator to the controller. And it is now, in the previous case, information, there wasn't any explicit use of information. In this case, there is an explicit use of information. Information flows through specifically constructed feedback loops. This is top-down action because the flow is determined by the high-level structure of the feedback loop. If you disconnect the elements of the thermostat, they're all there, all the elements are there, but you undo the one wire, it won't work because you've disrupted the higher-level structure while all the lower-level elements are unchanged. So this happens everywhere. Homeostasis in the human body, temperature, blood pressure, heart rate, transport across cell membranes, each is governed by implicit goals embodied in the physical structure of the body. The human body has thousands of such control systems in it. They occur at all higher levels in the hierarchy, and these feedback control loops have been built in through adaptive selection. And the interesting thing is the role of goals and dynamics. The nature of causality is different when feedback control systems are guided by goals. In standard physics, the equation of state and the initial conditions give you the outcomes. Now, the physics is fixed, the equation of state is fixed for a given system, so in standard physics we think of initial conditions giving you the outcomes. That was the case of the previous class. With a feedback control system, it's completely different. The physical structure and the goals determine the outcomes. It's the same physics, but instead of an equation of state, you have a physical structure. And the point is, for a given system, the physics is constant, the structure is constant, so the goals determine the outcomes, and the initial data is irrelevant. So this causation is completely different. The point of a feedback control system is precisely to make the initial data irrelevant. And so, in fact, the series of goals in a feedback control system are causally effective. They embody information about the system's desired behavior or responses. So living systems are goal-seeking or teleonomic. And I want to emphasize the goals are not the same as material states, for they are desired rather than actual states. Now, they will be represented by material states that will make them causally effective, but they themselves, the goal, is not a physical thing. A complex causal description must necessarily take these goals into account. They exist as emergent properties of the system. They're not embodied in any components of the system. And the mathematics is well-established feedback control systems, control theory, and systems biology. There's a well-established mathematics. The third type of top-down causation is adaptive selection, which is generation of adaptive states with new information encoded. So you have a set of system states, you have a fitness criteria and environmental niches, and from these system states, a preferred state is chosen. A selection agent selects this from all the states available, and you have a new system state, which is the preferred one. Some variation takes place, you have a new set of system states, and you go around the loop again. And of course, the classic example is Darwinian evolution. The development of DNA coding is a particular sequence of bases through an evolutionary process which results in adaptation of an organism to its ecological niche. This is a classical case of top-down action from the environment to the detailed biological microstructure, because through the process of Darwinian adaptation, the environment, with other factors, fixes the specific DNA coding. And the point about this, there's no way you can ever predict the DNA coding on the basis of biochemistry or microphysics. You're wasting your time asking a physicist to tell you what the coding will be. He can't do it. There's no way you could ever predict the coding on the basis of biochemistry or microphysics. You can't even ask the appropriate language. What happens is that polar bear is living in a white environment. In effect, the environment tells the animal that it's best to be white, not black. And through the process of Darwinian selection, the DNA sequence of that animal has got a code in there which tells the cur to be white, not black. If it was in the Canadian forests, it would have a different coding which would tell it to be black. And that is top-down action from the environment into the detailed sequence coding of the DNA. So that's the classic example. And this is the origin of biological information. It is the systematic use of meaningful information that distinguishes biology from physics. This information comes by adaptive selection of meaningful information from a much larger pool of random information, according to higher level selection criteria, hence top-down action. The selection criteria is a higher level thing than the system that is being selected. Throwing away all of the rest, leaving behind a meaningful set of data, and that's the mechanism flowing against the stream of increasing entropy. It is allowed but not explained by the interchange of energy with the environment. And Darwin's demon is what I like to call Darwin's demon is the analog of Maxwell's demon. It's the way that new information comes. What you've got coming up from the bottom there is a whole mass of disordered stuff, an ensemble of stuff, and there's a selection gate which leads through a subset of the stuff which is coming in. Selection then selects from a jumble in which everything that you need to know is there, but it's hidden in the ensemble because you don't know what is what. You select the subset that satisfies some selection criterion, and that gives you meaningful information, the chosen information, and it's obtained by discarding the information that is not meaningful. Selection is a process of discarding a huge amount of information to winnow out a bit which matters and is important. Local entropy decreases as order increases, and of course erasing information is a dissipative process, and the whole thing fits together and shows how new information comes into being. Various people have written mathematics about this. Holland's book, Adaptation in Natural and Artificial Systems, is a very good book on this. It happens in computers and neural networks and in evolutionary computing and population genetics. So there is a whole lot of mathematics which describes this. Now, things get interesting when you ask the question, where do the goals in a feedback control loop in biology come from? And the goals in the feedback control loop in biology come from adaptive selection. So you have a feedback control system in which the goals are adaptively selected. That is a higher order of causation. Now, so whenever the goals in a feedback control system are determined by adaptive selection, you have top-down causation into the goals, which then into the selection of the goals. Now, the classic example is Pavlovian conditioning in animals. Animal response to a stimulus such as a sound, which is taken as a sign of something else and causes a physical reactions, is implemented by motor neurons. The animals are trained, and the training is causally affected by top-down action from the brain to cells and muscles. The fitness criterion is avoidance of negative stimuli. How do you demonstrate its top-down causation? Change the conditioning, and the response is different. The really important one is in the human body, the genetically determined goals for blood pressure, temperature, and so on. Where did they come from? They came from adaptive selection. And so our blood pressure and temperature were determined through an adaptive process in our long past evolutionary history. Those goals were fixed by the process of adaptive selection. And so it's when the goals in the feedback control system are adaptively selected, you're starting to get really higher order behavior. And evolutionary game theory perhaps is a way to try to do this. Martin Nowak's new book is a way of trying to examine the mathematics of this. And then the topmost level of causation that we can be aware of is intelligent top-down causation, the effect of the human mind on the physical world. This is a special case of feedback control with adaptive choice of goals, where the selection of goals uses symbolic representation. It uses language and abstract symbolism, including mathematics. So this is when you have adaptive selection of goals, but now symbolism, language, and mathematics are taking a role in determining the way the goals work. And my example is aircraft design. The plans for a jumbo jet aircraft result in billions of atoms being deployed to create the aircraft in accordance with the plans. Now, it's a non-trivial example. It costs a huge amount of money to employ experts in aerodynamics, structures, materials, fuels, lubrication, controls to design and manufacture the aircraft. The plan of the aircraft is not equivalent to any single person's brain state. In fact, there's no single person who knows everything which happens in a jumbo jet aircraft. The plan is an abstract, hierarchically structured equivalence class of representations. It's an equivalence class because it can be represented by talking, it can be drawn, it's in computers, it's in brains. You can represent it in many different ways. It's not the same as any representation. The plan is the equivalence class of all of those representations. It's abstract, but it's causally effective because the aircraft would not exist without it. It could not occur without language and mathematics, as well as the social systems in which it's embodied. And so the jumbo jet, the existence of the jumbo jet is the result of top-down causation from plans, abstract things, through the human mind into material systems. So consciousness is effective, rationality and understanding is effective, feelings and intentions and understanding are effective, and social systems such as the value of money. Money is a piece of paper. It is causally effective because of the social system in which it is embedded, and that's what makes that causally effective. So concepts are not the same as brain states, as I've been trying to explain. They can be represented in many different ways. They're causally efficient. They affect the nature of physical objects in the world, and their function is based in neuronal structure enabled by the underlying physics. Now, a very interesting example is Maxwell's equations. I'm talking about the theory. Maxwell's theory, the equations of electromagnetism, is an abstract entity because the theory is abstract. It's something that physicists discovered by a process of experimentation and conjecture. The theory led to the development of radio, cell phones, television, and so on. The theory is shown to be true by experiments and by its technological outcomes. So that abstract thing, those equations, are causally effective. And again, they're not the same as any single person's brain state. And there's a wonderful book called 17 Equations That Change the World. It gives you 17 different kinds of equations, Maxwell's being amongst them, which have changed the physical world because Maxwell's equations have led to cell phones, television sets, you name it, all of those things. They would not exist if we hadn't had the theory which Maxwell gave us. And so those theories have changed the nature of the social world around us. The mathematics underlying how the mind works, there have been various attempts in neuroeconomics and other such things, but you better be cautious of them. The attempts to predict how the mind will work through mathematical models in the have been a bit of a disaster because they led to the financial meltdown when mathematical equations were being used. So this is the case, I think, where one must be extremely careful trying to predict what will happen in intelligent top-down causation by using equations is a perilous adventure. Okay, so now, How does this happen when physics is there at the bottom? How is there room for this top-down causation to take place when the physics is acting from the bottom? How can it happen? How is there room for this to take place? Firstly, it's because the functioning, according to the laws of physics, of the parts of a given system is determined by the context. I've already said this. Higher level conditions set constraints on the lower level operations. And the higher level purposes can conscript the physics to its ends by changing the operation context, altering the context-dependent constraints. The structure and boundary conditions affect the outcomes, and you can change them. And that's what happens in a computer where you operate it as a music system or a word processor. It's what happens when you move your muscles. You may be using your muscles to play football or to play music. Your brain is constraining what happens in your cells. But a very important point is top-down action. We do not just have invariantly functioning parts assembled in different ways and then operating in different contexts. What happens in top-down causation, the very nature of the parts, the way they function, is affected by the context. Indeed, they're often adapted to their higher level function. Now, for instance, a hydrogen atom is completely different in the wild than it is when it's in water. So, in fact, the nature of hydrogen is not the same in water and when it is free. Free neutrons is a very interesting example. If you have a neutron on its own, it decays with a half-life of 11 minutes. If you put it into the nucleus of an atom, it is stable for billions of years. Its nature is completely different. And the cells in the human body, the cells in the body start off by being pluripotent. They're all the same, and some of them specialize to skin, some to blood, some to hair, and so on. The nature of the cells changes to adapt it to its task in the body. This is a really important point. So this isn't the same as molecules just bumping into each other. It is a case of the parts being adapted to their purpose. The next thing is that, in fact, the bottom-up isn't deterministic because there's a lot of chance. There's quantum physics. We have coarse graining. There's quantum uncertainty. There's randomness at the bottom. And so the physical outcomes in biological systems isn't uniquely determined because there's a lot of randomness at the bottom level. And that randomness provides the openness needed for adaptive selection to take place. And in fact, there's a lot of evidence now that randomness is important in biological functioning. It's because of randomness that selection can take place. Without the randomness, there wouldn't be an ensemble to select from. The adaptive immune system is one example, and brain plasticity is another example. And the final thing is that top-down causation occurs because it occurs in physics. And this is not very well known. I give you there an archive preprint where I talk about this. The arrow of time is a classic example. The boundary conditions at the start and end of time determine the outcomes. The arrow of time is not determined by the microphysics. It's determined by global conditions. The arrow of time has to come from boundary conditions at the start of the universe because local physical laws are time symmetric. And another very interesting example is in quantum physics, state vector preparation, if you think about it, is an example of selection. For instance, the Stern-Gerlach experiment takes place by a non-unitary top-down process of adaptive selection of a mass of incoming states to polarized outgoing states. The key analytic idea is that of functional equivalence classes. I've mentioned this several times. Each equivalence class is a set of low-level states that all correspond to the same higher-level state. When you coarse grain, all of the lower-level states correspond to the same higher-level state, and entropy is a measure of how many lower-level states correspond to a specific higher-level state. And it's the higher-level states that get selected for when adaptation takes place. And so the claim that I would make is whenever you can identify existence of an equivalence class of lower-level states corresponding to a higher-level state, that shows that top-down causation is in action. You get the reliable emergence of high-level behavior. You have a high-level state H1 which can be realized in states L1, L2, L3 at the low level. The lower level dynamics moves L1 to L1 prime, L2 to L2 prime, L3 to L3 prime. You have an equivalence class when all of the resulting states give you the same outcome at the top. And so whatever instantiation of the high level one you have on the left, The lower level dynamics give you the same result on the right, and so there's an equivalence class below which gives you the same higher level action. So, the nature of causation. Aristotle was right. The key point about causality is that simultaneous multiple causality, interlevel as well as within each level, is always in operation in complex systems. Any attempt to characterize a partial cause as the whole, characterized by that little phrase, nothing but, is a fundamentally misleading position. Indeed, this is the essence, in my view, of fundamentalism. Fundamentalism, in my view, is claiming that a partial cause is the whole cause. One must acknowledge the entire causal web. And there are always multiple levels of explanation that hold. There's never a single explanation. So one can have top-down explanation as well as bottom-up, both being true at the same time. The example here is why aircraft fly. Now, from the bottom-up view, that aircraft flying along is because of the molecules impinging from below, which are moving slower than the molecules above. So Bernoulli's law says there's a greater pressure below than above, and so that's what makes the aircraft stay up in the air. That's the physics explanation. Correct. The top-down explanation of why the aircraft flies is it was designed to fly. And as I've already said, that's a very non-trivial example. It cost a lot of money to design it to fly. It would not fly if it hadn't been designed. If you get the design wrong, it will not fly. The same level view of why it's flying is because the pilot is flying it. He's sitting at the controls, he's opened the throttle, he's guiding it. And so the same level explanation is because the pilot is there. It's also because the timetable has said that the aircraft should fly at 10:32 from Krakow to Berlin, for instance. Those also, the aircraft would not be flying if the pilot wasn't there and if the timetable hadn't said it should be flying. And the topmost reason it's flying is because, hopefully, it's making a profit for the company. And it would not be flying unless someone thought it was going to make them a profit. These are all simultaneously true and relevant. It won't fly unless they all apply. The physics explanation is all very well, but unless you've designed it, there's nothing for the physics explanation to apply to. So Aristotle had the material cause, the formal cause, the efficient cause, and the final cause. From my viewpoint, you can adapt this to say the material cause is the lower level cause, the physical cause, the formal cause is the same level cause, the efficient cause is the higher cause, and the final cause is the topmost. So I think Aristotle was talking about top-down and bottom-up causation in the hierarchy of complexity. When does top-down causation take place? Well, bottom-up action suffices when you don't need to know anything about the context. In a simple system, details of the environment are irrelevant. Statistical physics gives you the answer. So, for instance, the perfect gas law is a macro law. You don't need to know the shape of the container, and the gas laws are okay. So that is a case of pure bottom-up causation. Blackbody radiation does not care about the shape of the container. That's bottom-up. Top-down causation occurs when the shape of the container determines outcomes. So, for instance, the vibrations of a drum or sound waves in a musical instrument. Rayleigh-Bénard cells in a heated viscous medium. The patterns formed by the reaction-diffusion equation. Physical interactions in the interior of a star. Whenever physical structures shape the lower-level interactions from the top, radio, computer, motor cars, and physics experiments. So, in fact, top-down causation is far more common and bottom-up. So the convection cells are determined by the shape of the boundary. The nuclear reactions in the interior of the star at any particular radius are determined by where you are in the star, which is determined by the global structure of the star. So those are examples of top-down causation. When is top-down causation very well proven? Between the mind and society, there's a big literature now on cultural neuroscience, which I could give you examples from. In the mind and the brain, vision works by top-down causation. I could talk about that. Environmental enrichment causes effects on the brain. There's a whole lot of examples from the brain. In physiology, Dennis Noble has written about the way top-down causation takes place in the way the heart functions. In evolutionary theory, as I've already mentioned, so top-down causation, there are many, many examples where you can't actually even do the theory without top-down causation. And the final thing I want to talk about is the cosmic context. Physics cannot give a complete causal account of what happens today from initial data in the early universe because random quantum fluctuations determined which galaxies would exist. You can ask yourself, could the content of this talk be implied by initial data in the very early universe, as some reductionists might have you believe? No, because quantum uncertainty makes this impossible, for even the existence of the Earth is not guaranteed by the data at the very early times in the universe. Quantum uncertainty means that the physical outcome is not uniquely determined, even in principle. Meaning comes into being in the expanding universe that did not exist at earlier times. Where did the meaning come from? It came about because the higher levels developed their own autonomous powers independent of the lower levels of causality and structure. It's this emergence of systems with their own causal, autonomous causal power which enables meaning to come into existence. And that is only possible because of the top-down causation. That's what enables this complex thing to it enables the higher level to be causally effective. So here's the expansion history of the universe, time going from left to right, the start on the very left at the Big Bang, and the inflationary period on the very far left, the dark era galaxies forming. And the point I want to point out, in the current view of cosmology, quantum fluctuations during the inflationary era led to the existence of galaxies today. That's all I have to point out there. According to the standard theory, it's quantum fluctuations which determined the primeval perturbations which gravitational attraction turned into clusters of galaxies and galaxies. Now, those quantum fluctuations are in principle unpredictable. Therefore, if you knew everything about the universe at that time, you wouldn't know that this particular galaxy, you couldn't predict that this particular planet would exist. So you couldn't predict that I would exist, so there's no way you could predict what I am saying. So that dream that full initial data will tell you everything, it's just we don't have enough computing power, that is not correct, because quantum uncertainty says that cannot possibly be true. And so that's what I wanted to say about all of this. I think that top-down causation occurs everywhere. It's crucial in the emergence of complex systems, and it's what enables us to have intelligence, to think in the way that we do.
Thank you very much for your fascinating and extremely extraordinarily inspiring lecture. We have not much time, but if there are some urgent questions, comments, so we are free. Please.
George, first a comment. I don't know if you're aware of Leibniz's philosophy, but when you were talking about our human body having literally thousands of representations of the external world encoded within us, this is exactly Leibniz's idea that we're monads. Each monad is a view of the universe from its particular point of view. So it's a fabulous vindication of Leibniz. The question is really, are you right to put so much confidence in what I might regard as a transient theory of inflation in the way you think about things? And in a way, the implication of Leibniz's philosophy is that there is an overall description of the universe. I mean, we are all views of the universe from our point of view, but there is one, and so to speak, if we were God, we are that universe, I think really is the implication of Leibniz's philosophy. So perhaps there is a global way of contemplating the universe which would put inflation in its place.
That may be. It's just, given that inflation is the current dominant paradigm in cosmology, I think this is a knockdown argument proving that the reductionist dream simply isn't even begin to be feasible. And so therefore you've got to ask, where did this order come from if it wasn't in the initial data? And it has to emerge, and the emergence can only be successful. Bottom-up causation can give you emergence up to the level of sand piles, of the reaction diffusion equation, a certain level of complexity. There's a ceiling to how much complexity you can get before you start getting top-down causation. Actually, we still don't understand how we made that transition. I was last week at a conference on how information got into life. We still don't understand how Darwinian evolution started. Once Darwinian evolution is started, you're on the way, and we do not know how we jumped over until top-down causation became really effective in generating information.
Are there some other questions?
Thanks, George. That's a very rich, stimulating talk. One of your slides, one of the last few slides, maybe a couple slides back, there was a statement that higher levels develop, I think it was, that higher levels develop their own autonomous powers. And I stumbled a little bit over the term autonomy there. Autonomy can mean a number of different things. But in this context, part of what the higher level powers do is select from among the possibilities made available by the lower level structures. So there's a sense in which they aren't autonomous. They always work with given materials at lower levels. They're not simply determined by those lower levels, but the lower levels set, as it were, the space of possibility within which selections are then made at higher levels.
I think we'll need to talk about this. I think we're saying the same thing in slightly different language. I'm saying that the topmost level is not, what I mean by autonomous, it's not determined by the lower levels. It has its own, the logic at that level is able to function and is not controlled by the lower level logic. And that is enabled precisely by that mechanism you're saying, by selection. That happens all over the place in the way the mind works. It's crucial.
Thanks.
George, just one question about top-down causality in the very early universe.
Yeah.
In some sense, it seems like there's a very different type of top-down causality there, because in some way you have relationships, whatever inflatons or potentials are in the early universe are governed in some sense by relationships.
Yeah.
And those relationships really dictate what is possible and what isn't possible, even though there's a large, they constrain the particular statistical outcomes that can emerge, right?
Yeah. Yes, I agree.
Okay.
I feel very sorry, but the arrow of time does not allow us to continue discussion.